Imagine looking into a mirror that does not show your reflection, but instead reveals a memory from billions of years ago. That is, in a sense, what the James Webb Space Telescope allows humanity to do. When Webb observes extremely distant objects, it is not seeing them as they exist today. Their light has traveled across the expanding universe for billions of years before reaching the telescope. Every photon carries information from an ancient moment in cosmic history. This makes Webb far more than a powerful camera. It is an instrument for studying the early universe and examining how the first stars, galaxies, and large-scale structures emerged. According to the standard cosmological model, the universe began approximately 13.8 billion years ago in the event known as the Big Bang. As the universe expanded, it cooled. Particles formed, followed by atoms consisting primarily of hydrogen and helium. Then came a period often described as the cosmic dark ages. There were no stars shining through the darkness yet. Gravity slowly began gathering matter into denser regions. Over enormous periods of time, these regions collapsed and eventually produced the first stars. Those early stars became the foundation for the first galaxies. For a long time, scientists expected this transformation to be relatively gradual. The earliest galaxies should have been small, irregular, and relatively primitive. More complex structures were expected to develop later as galaxies merged, formed stars, and accumulated more material. Then Webb began looking deeper. Some of the distant galaxies it observed appeared surprisingly bright and developed for their early cosmic age. Researchers found galaxies displaying substantial structure at times when the universe was still extremely young. These observations did not automatically overturn the standard cosmological model. Instead, they created new questions about how quickly galaxies could form stars, accumulate mass, and develop organized structures. Astronomers also use the light from these distant galaxies to investigate their chemical composition. This provides another important clue. The early universe was dominated by the lightest elements, especially hydrogen and helium. Heavier elements such as carbon and oxygen were produced later inside stars and distributed through space by stellar processes. So finding evidence of substantial chemical enrichment in very early galaxies tells scientists that generations of stars may have formed and evolved surprisingly quickly. The young universe may therefore have been more active than older models suggested. Stars could have formed in dense environments, lived relatively short lives, and returned newly produced elements to surrounding space. This process would help explain how increasingly complex chemistry appeared throughout cosmic history. Another major mystery involves supermassive black holes. Modern telescopes have found evidence for massive black holes in the early universe, raising questions about how they reached such enormous masses so quickly. Under some traditional scenarios, black holes begin relatively small and grow by consuming surrounding matter or merging with other black holes. But the existence of extremely massive objects at very early times challenges scientists to understand whether their seeds could have started much larger or whether some early growth processes were far more efficient than previously expected. Researchers are exploring several possibilities. Some models suggest that certain black holes could have formed directly from extremely dense regions of the early universe. Other ideas investigate whether unusual environments or interactions involving dark matter could have influenced their rapid growth. None of these possibilities should be treated as confirmed answers. That is what makes Webb's observations scientifically valuable. They do not simply provide conclusions. They reveal gaps in our understanding. And the deeper Webb looks into cosmic history, the more researchers are discovering that the early universe may have been far more dynamic, complex, and rapidly evolving than anyone once imagined. The mysteries do not stop with the first galaxies and massive black holes. Some of the most fascinating questions involve the structures those early systems developed. Scientists once expected the young universe to appear relatively chaotic. Instead, Webb has observed distant galaxies with surprisingly organized features. Some show compact bright centers. Others display shapes and structures that provide evidence of complex stellar activity. These observations raise an important question. How did such organized systems develop so early? One possibility is that galaxies can assemble and evolve much faster under certain conditions than older models predicted. Another is that scientists still do not fully understand the role played by dark matter. Dark matter cannot be observed directly through ordinary light, but its gravitational influence is believed to shape the distribution of visible matter throughout the universe. Rather than being merely a passive gravitational framework, dark matter may have played a critical role in helping early matter gather into the structures that eventually became galaxies. Understanding that process could help explain why some early galaxies appear so developed. But Webb is also revealing another fascinating aspect of the ancient universe, its chemistry. Astronomers can detect molecules and compounds in distant regions of space by studying their infrared signatures. Some observations reveal carbon-containing molecules within interstellar environments. These molecules are not evidence of life, but they demonstrate that chemically complex material existed in the universe long before Earth formed. That is an extraordinary thought. The raw ingredients involved in planetary chemistry were already present during earlier stages of cosmic history. As generations of stars formed and died, they enriched surrounding space with increasingly complex elements and molecules. Eventually, some of that material became incorporated into new stars, planets, and other systems. Our own solar system is part of this long cosmic recycling process. The atoms that make up planets and living organisms have histories that stretch back through multiple generations of stars. This means that studying distant galaxies is also, indirectly, studying the origins of the material from which worlds like Earth could eventually form. And this is where Webb's observations become especially profound. The farther the telescope looks, the further back in time it sees. Instead of observing the universe as one finished structure, Webb allows scientists to examine different stages of its development. Ancient galaxies show how quickly stars and structures emerged. Supermassive black holes reveal how extreme objects could form surprisingly early. Spectroscopic observations reveal how quickly chemical complexity developed. Together, these observations provide a much richer picture of cosmic history. But they also demonstrate how incomplete our understanding remains. Every unexpected galaxy creates another question. Every unusually massive black hole demands another explanation. Every chemical signature gives scientists another clue about how the universe became chemically complex. This is not evidence that established science has failed. It is how science advances. Models are built from observations, tested against new evidence, and refined when the evidence reveals something unexpected. James Webb has therefore done something more important than simply taking spectacular photographs. It has expanded the boundaries of what humanity can observe. Every photon reaching its detectors has traveled through an enormous stretch of cosmic history. Some of that light began its journey before Earth existed. Long before humans appeared, those photons were already traveling through space. Now they arrive at Webb carrying information about ancient galaxies, stars, black holes, and the environments from which later cosmic structures emerged. We built Webb to look deeper into the universe. But the deeper we look, the more complicated the story becomes. Perhaps future observations will resolve many of today's mysteries. Perhaps new models will be required. And perhaps some questions will remain unanswered for generations. But one thing is certain. The universe still has chapters that humanity has never read. And every ancient photon captured by James Webb gives us another opportunity to turn the page.